All right, so by now you're probably bored of seeing graphs and chi-square tests and so on, but I promise you this is the last graph and the last test that's gonna come after this. And we thought this was the most interesting graphs because there's so much difference between all three samples. So this shows the average moves for ties, white win, and black win. So how many moves did the strong computer play when it won as white, when it won as black, or when it played a tie? Same goes for the weak computer. So white win, black win, tie, and professional play. How much did it play? How much did the professionals play when they played white, how many moves did they play when they played black, and how many moves did they play when they played a tie. So as you see, for the strong computer, it's 67.88 moves for when the white player wins. So right off the bat, we see that the values for the strong computer, the average moves, are way higher than all the other ones, and we're not sure why this is, and we can't actually say anything. We can't say why it is, but we can speculate that this is because the computers are so evenly matched, and they just play to win, regardless of how far they may be behind. So they never go for draws. They never, like a pro player, for example, he would accept a draw at one point when he sees the game is hopeless, even though they could potentially still continue playing the game. So it draws out the game a lot. Therefore, the average moves in general are way higher. And the reason for white win being the lowest is just we speculate that because of the advantage that white has, he's probably going to win in less amount of moves. And black win is a bit higher, and then tie would be the highest because we believe that this is because the ties mostly on the computers or on the strong computer were when moves were repeated multiple times, and not when there was an actual official stalemate. So it just increases the amount of moves in total, and so that's why the ties are the highest. Now for the weak computer, we have 34 moves, exactly 34, because every single move or every single game that was played where white won had 34 moves, which we have already previously discussed and thought it was very weird. Now for the weak computer, the black win amount of moves is very low. It's at 22, and this is a clear outlier because there were only two games where black won, and one ended in 14 moves, which is extremely fast, and one in 30, which is pretty normal but still pretty fast game. So it averaged out to 22 being very low, and for the ties there were 50. So again, there's not much to say about the weak computer. There's, like we have already often mentioned, it was just pretty ridiculous games that were played, but nevertheless it was interesting to see it. For professional play, we see that white again has, similar to the strong computer, has the lowest amount of moves, and it is shared, though not like with the strong computer, shared with the ties, which have extremely similar amount of moves. And this is because so first of all, white wins in lower amount of moves, as we did previously discussed, because of the initial advantage that white has. So white is more likely to win the game faster. And the reason for the ties being lower is because I also sort of alluded to that before, was that players are able to see a lot of moves ahead and are able to see that the situation is hopeless and that there's no reason in continuing to play the game because they've already calculated the next, who knows, 10 moves or 15 moves, and therefore just end it in a draw. And black again has more moves than white because black is at its disadvantage, so it has to fight its way. Has a longer way to fight to win, therefore has more moves. All right, so here's our last test, and it is a chi-square test for homogeneity of the populations for proportion of the average number of moves for ties, white wins, black wins amongst the three samples. So our null hypothesis was that P1 is equal to P2 and equal to P3, so the strong computer is equal to the weak computer to the professional play, specifically the proportions of the average number of moves for the ties, for the white wins, for the black wins. So here are our observed counts. So these are just this data is directly taken from the graph. As you see, the average number of ties for the strong computer is 67.88, and then for the weak computer was 34, etc. So what is important to remember about this test is we're not looking if these numbers are different. So we're not looking to see if 67.88 is different than 34 and 73.53 is different to 22. But we're looking if the proportions are different. So the proportion 67.88. So I'm looking in the strong computer column. So 67.88, 73.53, 75.58. So as you saw on the graph, it was like this ascending sort of thing. So we're looking, is this sort of ascending, or is the total sort of ratios equal amongst all the graphs or amongst all the samples? And we already saw that in the graph that this was actually, there was some inconsistencies, or there was a lot of inconsistency. So obviously the moves were different, but again, that's not what we're looking for. We're looking for the proportions. So as you see for the weak computer, it has 34, then it has 22, and then it has 50. So it has like a middle, and then it goes down, and then it goes up again. Whereas for the strong computer, it was up, up, up. For professional games, it's 43. So it's middle, then it's up, and then it's down again. So we're testing to see if these proportions are different. But now, as I just explained, that you already see that it is very likely going to be different, and we're probably going to reject the null hypothesis. So here are our expected counts. So you have 68.26. So that's very close to the 67.88 that we had before. You have 69.25, which is rather close to the 73.53 from our observed counts. And so for the strong computer, the results are actually pretty similar. So the expected counts are pretty similar to the observed counts. But for the weak computer, we had 34 for the first row, where now it's 33.45. Again, very similar. But then for the second row, we had 22 for observed, where we have 33.94. So we have a pretty reasonable difference. For the last column, so average number of moves for white wins, for the weak computer, our expected is 38.95, but our observed was 50.33. So again, a reasonable difference this time in the positive direction. For professional games, we also see quite some differences, but for the first expected count, we have 43.46 compared to the 43.28, so extremely close, almost right to the number. But for the second one, we have expected 44.09, where it was previously 51.75, so quite a large difference. And for the last, we have expected 50.60, whereas our observed was 43.12. So already we can see that there's a lot of differences. The first column for the strong computer was very similar, as you saw this ascending. Even the expected counts are in this ascending order, like were the observed. But for the weak computer and professional games, we already start seeing some differences. So here is our p-value. It is 0.01. So we reject the null hypothesis that the number of average size white wins, black wins is equal amongst the three samples due to our low p-value. Like the graph concerning this data portrayed, it was clear that there were differences amongst the three categories. This was the only test that used the weak computer as a population, which is important to take in consideration, since the weak computer had obscure results. Nevertheless, we see that the proportion of average number of moves played is different for ties, black wins, and white wins. It is important to remember that the test does not show how the average number of moves are different amongst the three samples, but rather how the proportions are different. Looking at the observed counts, you can still clearly see the strong computer play by far more moves per game, while the weak computer and professional play had similar average number of moves per game. So that is it, and I hope you enjoyed all these tests.
Hey guys, I hope you enjoyed the video and the stats project. You have to remember that this is only applicable for the Mac chess application, so our simulations that we did. Also for the professional chess games, all our hypothesis tests and confidence intervals and graphs are only applicable to those professional games that have an ELO of 2,700 or more. And some of the most important things from our project that you may want to remember is that the e-file pawn move that the white player can begin with, which is the most common move, so you'd think that it has an advantage, but as we found out, it does not have a significant advantage. Also on the Mac chess application, the weak strength computer versus another weak strength computer has very bizarre results, as in 75% of the time there's draws, black only won twice, that kind of thing. Also remember that for the pro games, white had a 0.32 win ratio, where black only had a 0.16 ratio, which means white was 2 times more likely to win a game. Some more things that we could have looked at but weren't able to in this project were testing professional games with different ELOs, so for example 2,500 and more, or between a range of 2,200 and 2,500 or something like that, which could have given us different results. Also, we could have tested different simulation difficulties. As you saw when I showed you the chess application, it was a slider and we just took the two extremes, but there's also difficulties in the middle that we could have tested and could have been a lot different. Thanks for watching the video. I hope you guys enjoyed it. I hope you guys thought our project was interesting. Shout out to Mr. Draft, and thanks for watching the video. Bye.